Dr. Leon.
Good day, my name is Lilion and I'm here to present my research, Aggregate Angularity Effects on Mechanical Properties of Asphalt Concrete. Asphalt concrete is a material or mixture made up of aggregates, asphalt binder, and air voids. The aggregates make up 90 to 95% by volume of the asphalt concrete mixture. Hence, its influence on the behavior of the asphalt concrete material. And these mechanical properties or mechanical behaviors are elastic, compressive strength, the permanent deformation, as well as the fatigue life of a mixture. Now, because of the volume or the percentage of the aggregate within a mix, the research is focused on a particular property of the aggregate, which is the angularity. And angularity was defined in 1932 by a geologist as whether aggregate particle edges are sharp or rounded. And it was further refined by civil engineers and mechanical engineers as the change between a particle radius in a particular direction and that of an equivalent ellipse. Now, this definition was incorporated into a device for measuring the aggregate angularity of particles within a asphalt concrete mixture, and this device was the AIMS, which is the Aggregate Imaging System, and it classified the aggregate angularity into rounded, sub-rounded, subangular, and angular using an angularity index, 0 being very round, up to 10,000 being very angular. And these are the 4 classifications we are using within this research. So the objective of the research is to evaluate the aggregate angularity ranges and the effects on laboratory stiffness, compressive strength, and creep deformation mechanical properties of asphalt concrete. The methodology of this research was a very extensive one and very time consuming. The sample preparation was the most time consuming aspect of the research, and then we move on to the compaction and then the performance testing. So in the sample preparation, the mix was designed using local requirements for dense graded mix. However, the difference with this research mix is that all the coarse aggregate particles were replaced with the 4 different categories of angularity. So we had mixtures with only rounded coarse aggregate particles, those with sub-rounded particles, those with angular particles, and subangular particles. Because we wanted to see the behavior of, from a very round mix to a very angular mix, what happens in terms of the mechanical properties. And then from the sample preparation, the aggregate and binder was mixed and compacted to 3 different heights using gyratory compactor. And these heights were 63.5, 100 millimeter, and 150 millimeter. The diameters were the same of 100 millimeters. The gyratory compactor was used to control the air voids as well as the heights. So we didn't want any variation in the air voids, so the air voids were compacted at 7% air voids. And then we moved to the performance testing, where we had a number of tests, which is the stiffness test, the compressive test, and the creep test. And these tests were done at temperatures from 25 to 40 degrees for the 4 different mixes, and the heights of 63.5 to 150 millimeter. And then for the creep test, we further added a variation, which is the loading that was used for the test. So 70 and 200 kVA, 70 being the tire pressure of a particular car. Also to know that the 100 and 150 millimeter diameters, the heights were similar to that height, the heights used for asphalt layers in the pavement structure. So the first test was the tensile stiffness test. Indicated that there was no significant influence on the stiffness based on the change in the aggregate angularity. And this test was done at 25 degrees. Now this supports the theory that the binder has significant influence on stiffness, because the more viscous the binder, the lower the stiffness modulus. The stiffer the binder, the higher the stiffness modulus or mix. Now these properties are very important input in pavement design. Then we move on to the compression test. The compression test was to evaluate the failure and also the compressive strength of a particular mixture. And we use 100 millimeter and 150 millimeter heights. And then we validated the results using the Moore-Coulomb circle theory. And we found that the mode of failure was being true shear failure, with an average failure shear angle of 64 degrees and a friction angle of 32 degrees. And the friction angle was close to that of granular material, although an asphalt concrete is not a granular material. And then we move on to the compression test. And the compression test was done to evaluate the compressive strength as well as the tangent modulus of the mix. And it showed that as angularity increased as indicated by the index, so does the compressive strength and the tangent modulus of the asphalt concrete mixtures. And this was so for both the 100 and 150 millimeter heights samples. And then we move on to the last two tests, which were the static and repeated load creep test. The creep test indicated that at low temperatures, angularity did not have a significant effect on deformation. However, at high temperature, angularity does have an influence on the resistance of asphalt concrete to deformation. And it should note that permanent deformation tests or deformation tests are done at high temperatures to see the influence of binders as well as aggregate on the deformation or the deflection or the movement of the asphalt concrete layer. So to conclude, the stability of pavement mixtures increases with an increase in the angularity of the aggregate in a flexible pavement. This is true for all cases of stress levels, sample heights and temperatures. Current minimum criteria for aggregate angularity in flexible pavements influences the mix design, the construction costs, and the asphalt performance. Hence, the enhancement of an aggregate angularity criterion, which is important for road and highway organizations. Thank you.
Thank you, Dr. Leon. Do we have any questions for Dr. Leon?
Hello.
Yes, we have one question here. Most of the local aggregates have more angularity?
It all depends. Are you hearing me clearly?
Yes.
Yeah. It all depends on the manufacturing process and also the property of the aggregate, the hardness property of the aggregate. Because during the manufacturing process, how it breaks will influence how angular, how rounded it is, and also how you obtain the aggregate. Because if they dredge the aggregate, it will be more rounded than if they actually crush the aggregate. So for asphalt concrete material, the design concrete design they use mainly limestone material. They can use andesite material, which is mostly from Tobago. So depending on the hardness of the material and the manufacturing process, you can have the change in the angularity of the particular mix.
Okay, one other question, Mr. Dr. Leong. How does your research inform the local HMA mix design?
That's a very important question. If we all notice, those who drive or move from Trinidad notice the amount of defects, especially rotten, they have in the pavement and structures, we realize that it might be the construction process, it might be the design process. So it influences the design process, because that's what we engineers, most engineers can control. However, the requirements locally for accepting aggregate angularities based on a AASHTO or ASTM standard, which looks at the fractured faces. Now, this is a very biased test, because it's depending on the personnel to decide whether they think it's angular, or they have one fractured face or two fractured faces. And like if you have the AIM system, which is computerized, which removes the bias and gives you the exact angularity. So it helps inform the agency that the requirements for angularity needs to change. It needs to have a more robust definition of angularity, and which can influence also the prediction of permanent deformation, and also influence the stiffness of the material, which is a major input into the design of pavement structure. So it is something that well, I would say policymakers, as well as the people like Pure and Ministry of Works, need to check, reevaluate their policies in terms of acceptance of materials locally, because most of our codes or requirements are based on international codes, which are we use a different material to develop the code, but we do not have. It does not really account for the local material we have, or even the local process or manufacturing as well as construction process we have. So it does influence, and does have a major influence on the design of HMA pavements and mixtures.
Finally, do aggregates with higher angularity need higher quantity of binders?
From what I have noticed, it does not. When you increase the quantity, or whether you have the fines or as coarse aggregate, that's when it really changes. If the absorption rate of the material is still the same, if the surface area of the material is still the same, it will not really affect the quantity of the binder. Degradation will affect the quantity of the binder, because where degradation, you will have to have enough binder to reduce it to the acceptable void ratio, which is 4% for mixed design, or 7% for when you have field compaction. So it doesn't really affect it by that much.
Okay, thank you. We don't seem to have any more questions. Professor Ray?
Yeah, Dr. Leon, is a very good presentation. Just wondering that if you have tried to do developing any equations out of these experimental data.
Yes, one of my research, well, this what I presented today was just a chapter, one of the chapters out of 8 chapters of a research I was doing, and the major objective of the research I was doing was to develop an equation to predict permanent deformation based on angularity. So if I have the angularity of the particular aggregate, I can give an estimate of when, in terms of the number of loading application, when will that sample reach its allowable deformation. So I actually developed an equation using angularity parameter, as well as the other parameters we use locally. But angularity was one of the major inputs into the predictive model.
Great. Thank you. That's all my questions. Yeah. So I appreciate Dr. Leon for presentation and good answers of the questions.